So, in fun tales of things that may or may not have happened, Newton was sitting beneath an apple tree. A big old apple hit him in the head, and he started thinking about gravity and the amount of energy being used and things like that. Now, the reason I bring that up, everything we observed early on having to do with units happened at the macro scale and were things that we could observe directly. And most things we can observe directly end up being versions of work. Work is when we're going to be using energy to move something around. All these microscale things, like making and breaking chemical bonds, we certainly didn't get to see originally. So what I want to do is I want to set up all of our context for energy. Here at the macro scale, we'll start winnowing down to smaller and smaller scales, and eventually we're going to stop talking about work so much in this chapter, and we're going to talk more and more about the kind of energy we typically talk about as chemists. Now, let's start out by defining what work is. Work is the force needed to move an object a certain distance. So this pen, when I lift it, I'm using force to move this mass a certain distance. And it's being lifted against gravity. Now when we unpack it like that, we can start putting together an equation for it. So we can say work is going to be force times distance. And if we get more picky with force and expand it out a little bit more, we'll see that force is going to be mass times acceleration. So the amount of mass I'm lifting against gravity, and remember gravity is an acceleration force, and the distance that I move it, those three things together give us work. Which means that we can't do work in a vacuum. So if we use the everyday definition of work, we'll make the astronauts very sad because they're working very hard by the everyday definition. However, in terms of the physics definition, they're not doing a lot of work because they're not moving against much gravity. So keep that in mind. We have a big distinction between the scientific word work and the everyday word work. Now, the units for energy that we're talking about are going to be joules most of the time. And joules are actually a compaction of what we'd have in this sort of an equation. We're going to take kilograms, and it's going to be meters, the distance that we moved it, times the acceleration that we moved it against. Remember, gravity is 9.8 meters per second squared, times the distance you went. That would be these two pieces together, giving you meters squared over seconds squared. So kilograms, meters squared, seconds squared. You will be sick of writing this after about 2 problems. So just imagine how all of the professionals in the field feel. They got really sick of it too. So instead of having to write this out every time, we've compacted that to be what I like to call a mega unit, a unit that has other units hiding inside of it. And this particular mega unit is called the joule. Now, a joule is a fairly small amount of energy. There's much smaller versions for sure, but the SI unit, joule, is unwieldily small to use in a lot of the chemistry that we're going to do later, and also at a lot of the macro scale we're going to work at. So instead, we're going to talk about kilojoules as being kind of the native version that we're going to use most of the time. That does not mean joules stop being the SI unit. Joules are the SI unit. Kilojoules are the practical in chemistry scaling of that unit. But it turns out it's not the only practical consideration we've got as far as units go in chemistry. We also use the calorie a lot. So when you pick up a candy bar, you'll look at the label and it'll tell you how many calories are in it. Fun fact, if they're doing the label correctly, calorie will be spelled with a capital C. And that's because a capital C calorie actually contains 1,000 real calories. And these are written with lowercase. And 1,000 calories that we use in science is 1 kilocalorie. In other words, capital C calorie is a kilocalorie. So that's one way that science is messing with us a little. On top of that, if you go to some other countries, you'll find both calories, actually kilocalories, and kilojoules listed on the label. So you'll be able to find out how many kilojoules per mole or kilojoules of energy are present in the candy bar. Usually it'll be kilojoules, not kilojoules per mole, but we will use that in science in both ways because we use large numbers of molecules. That's why we have to use the big counting unit, of the mole. So you'll see it both ways as we go through these pieces of this chapter. Make sure that you're aware of these conversions. We'll always have them for us on exams and things. I do want to point out that 1 calorie equals exactly 4.184 joules. And that means that there will be no impact on your sig figs when you do that conversion factor. Both of those can be treated like they have infinite sig figs because it's an exact conversion.